Hello again. Hope everybody's doing well and you had a nice weekend. We're going to keep moving forward with Chapter 10 and the mole. Section 2 brings in a new concept that's really important, converting from mass to moles. Remember, in order to do that, do equations, do reactions, I should say, you have to have the right number of pieces to recombine. This section explores how you do those calculations. So you need your calculator. The picture to start this section is a picture of a jar of jelly beans. Normally this time of year you might be seeing those around places like the Junction and other stores where you guess the number of jelly beans in the container and win an Easter basket. Probably not going to see those this year, but you probably are familiar with that concept. If you knew the volume of one of the jelly beans and you know the volume of the container, you can kind of guesstimate how many might be in the container. It's the same kind of thing we're doing is as chemists. So one of the things we have to do is convert mass into moles and moles into mass. So mass, of course, is in grams. Moles is just our counting unit. So an easy example is converting inches into feet or feet into inches. Same sort of idea. You're going to have to divide by 12. Sometimes you're going to multiply by 12, sometimes depending on what you're trying to accomplish. Same kind of thing for chemists. Sometimes you multiply by 6.02 times 10 to the 23rd. Sometimes you divide by it. And in this case, we're actually going to be using molar mass of the substances to figure out how many moles of that substance we have. When we're using the molar mass of an element or a compound, remember the masses for elements are on the periodic table. If you're doing a compound, you have to calculate the molar mass. That's a problem within the problem, if you will. So if I want to go from the mass into moles, this is what your textbook has shown as their little roadmap. The question, the problem you might be trying to solve is asking you to solve for moles. They would have had to give you the mass of the element or compound in grams. And then you need your, that's the given, then you need your conversion factor. Remember, those units seem like a big burden when you're doing problems, but it will help you, I promise. It makes it so much easier. Pack the units around with you. So if we set it up with 1 mole on top and the mass of that particular substance in grams on the bottom, which again we get off the periodic table, grams will cancel grams and you'll be left with moles, which is the asked for unit for your answer. Again, you're going to have to, for compounds, calculate the molar mass. It's a little extra time. They'll usually just give you the formula of the substance. It really doesn't matter what the substance is. Even if you've never heard of it before, you can still do it. Look at the periodic table. So one more time, if they're asking you to find mass, this is the same process, only in reverse order. That's grams, so you have to get that straight in your head. Grams is for mass. They'll give you moles in the problem. And then our conversion factor is going to have mass on top, whatever that comes out to be, whether you can just get it directly off the periodic table or you have to calculate it for a compound. And this time 1 mole's on the bottom. So this time we're multiplying by the mass instead of dividing by it. But again, you won't get confused if you pack units with you everywhere you go. So moles on the bottom, moles on the top. Remember, this could be over 1, like 2 fractions. You're left with mass in the numerator, which is in grams, and that's what you have to report in your answer. The next concept, and this is actually, honestly, this was done first, is working with gases back in the 1700s. Avogadro was playing around, as we already know, and gases were all the rage. They were the cool thing to be experimenting with. One of the things that people found out is that when they realized that there was stuff in the air wasn't just one thing. They started doing some research, and out of that came actually our atomic ideas. So again, Avogadro's hypothesis states if you have equal volumes of different gases and they're at the same temperature and pressure, big caveat there, they're going to have the same number of particles. Now, on average, gases are at least 10 times their own diameters apart from other gases at normal atmospheric pressure. So they're mostly nothing. Gas is mostly nothing, as you can probably figure out. And this is going to be the kind of diagram, and we'll see a lot, little dots for gas atoms or molecules. These are little smaller ones here representing like the solid state where they're all touching. The longer the tails on these diagrams also is supposed to indicate speed, just an FYI. So again, the volume of a gas changes with temperature. You guys know that. This is a picture of a balloon, kind of like what that gentleman did in the movie we watched earlier that had liquid nitrogen poured off of it, poured onto it, not off of it. Oh my goodness. And it shrunk, right? Why did it shrink? Well, the gas particles got colder. That means they had less kinetic energy. That means they got closer together. And so the balloon collapsed. You can do this at your house, actually, if the sun ever decides to come out again. Take a balloon, blow it up, put it in the windowsill. And on a hot day, on a sunny day, the balloon will actually get bigger during the daytime and get smaller at night. You could try and put it in the freezer. It doesn't work that great in the freezer. Liquid nitrogen is definitely the way to go. Anywho, this is something we probably, many of us have experienced living in the foothills, driving to the valley or going up on the pass up to Dodge and then coming back to Sonora or down all the way to the valley floor. An inflated bottle tightly capped, a bottle that's quote unquote empty, but it's full of air. When you bring it back down to sea level, it collapses. And of course, this is a little deceptive. 3,600 meters is actually about almost 1,200 feet in the air, way higher than our passes, actually. But you've probably had something like this happen. If you take a sip of your water, put the cap back on, drive back home from Pinecrest or Dodge, and then your bottle probably won't be quite that compressed, but same idea. Also, some of you probably had things, I don't know if anybody's ever had their shampoo bottle or hand lotion explode in their suitcase on a jet flight. I have. It's no fun. Put them in a Ziploc bag. But if you take a bag of chips up to high elevation, the bag puffs up. And that is because there's less pressure on the outside of the bag, a constant pressure on the inside. Still have the same number of particles though. So the same number of particles, even if the temperature stays the same, if the atmospheric pressure changes, the volume will change. Why did I go in this big lead up? Because gases are dependent on temperature and pressure, and you have to keep that in mind. We'll get into gas laws later. Some of you have seen hot air balloons before. They have a small propane heater that just heats the atmospheric gases. It's not anything new. It's not like the Hindenburg where they put hydrogen in or anything crazy. But hot air ballooning competitions are always in the morning, and that's because the air is usually coldest in the morning, the surrounding air. And so by heating up the air inside the hot air balloons, then they can float better in the denser atmospheric gases. Again, because the volume of a gas changes with temperature and pressure, we had to kind of standardize it. So this little thing, write this down, STP, standard temperature and pressure, is the set of conditions you have to memorize, basically. So STP, what is that? It's a temperature of 0 degrees Celsius. freezing point of water, and a pressure of 1 atmosphere. Well, 1 atmosphere makes it easy to understand, but I want you to get this number in your head for when we get to gas laws. 1 atmosphere pressure is 101.325 kilopascals, and we'll come back and explore that in more depth in coming chapters. Again, that's 1 ATM or 1 pressure. It's not automated teller machine. It's an atmosphere pressure. So I have a box like this. Mine's actually not solid black, but 1 mole of any gas at STP occupies 22.4 liters, and that's the size of the box. You are familiar with a 2-liter soda bottle. A gallon's basically 4 liters, so this is like 5.5 gallons, if you will. Kind of weird way to think of it, but 1 mole of any gas at STP will take up 22.4 liters, as long as it's 0 degrees Celsius and 101.325 kilopascals. And of course, we have to do calculations with that too. So if they're asking you for volume, they're going to have to give you moles, and you're going to need a conversion factor, and that conversion factor means the asked for unit on top and the given unit on the bottom. And then you can cancel moles, and you're left with liters for your volume. All right, got your calculators ready? Let's try a couple. Oh, one more thing. Density. You know DMV. Density is mass divided by volume. Mass is measured in grams. Volume is measured in liters. So grams per liter. If we got a sample of gas and calculated its density, it doesn't matter what size sample it is. It doesn't have to be exactly 22.4 liters. But if we could get its density, so there'd be a number here, we can then multiply, if it's at STP, that's another thing that they don't really emphasize in the book, you could then multiply the density times molar volume, 22.4 liters per mole, and the liters would cancel. So your experimental measurement on a sample of gas you've collected, knowing that this is true for all gases at STP, and again assuming that your measurement is at STP, you can then have grams per mole, which of course is molar mass, which is how the molar mass of most gases were figured out. Taking a sample, taking this concept, and multiplying together. All right, here's the problems. So I need you to get your calculators, and you can pause this obviously because you're working on your own time. The question is, what's the volume of these gases at STP? So they're asking for volume. Both A and B have moles as the given information. So this is a really small amount of carbon dioxide, and you could put it into your calculator with scientific notation. That's your given. So you need a conversion factor that has the asked for unit volume over the given unit moles, and you know that's molar volume, 22.4 liters per mole. So if you take this number and multiply it by your conversion factor, remember per 1 mole, the one's here underneath the division line, and you'd end up with 0.0717 liters. Both of these numbers have 3 sig figs, so you should get to 3 sig figs in your answer. Next problem's the same, except without scientific notation, same process, 3.70 moles. Again, moles is what's asked for. You need an asked for unit liters or a given unit moles. Multiply those two numbers together, and you get 82.9 liters when you round it to the correct sig figs. Last thing in this section I would definitely copy down as your notes is the roadmap for finding moles. Notice just a couple things really quick. Okay, so if we want to go from mass to moles, you divide by the molar mass, which is the same as multiplying by 1 over it. If you want to go from moles to mass, you multiply by the molar mass. Molar mass is on top, moles are on the bottom, they go away. Same kind of thing if you're dealing with volumes. These are the kind of conversions we do all the time. If you want to go from a volume to moles, you divide by 22.4. If you want to go from moles to volume, you multiply by 22.4. And then finally, particles, which is what we did in section 1. If you have a number of particles and you want to get to moles of those particles, you're going to divide by 6.02 times 10 to the 23rd. If you want to go from moles to particles, then you multiply by 6.02 times 10 to the 23rd. This is the final version, or the complete version of it, and you just need to remember that moles are the heart of chemistry. And I heart you, and I hope you're all well. Take good care. Till next time.